Hello, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, I could go on ad infinitum. This is the beginning of the Fibonacci sequence, a string of numbers named after, but probably not invented by, the 13th century Italian mathematician Fibonacci. It may seem like a piece of mathematical arcana, but the Fibonacci sequence is found to appear time and time again among the structures of the natural world and even in the products of human culture. From the Parthenon to pine cones, from the petals on a sunflower to the paintings of Leonardo da Vinci, the Fibonacci sequence appears to be written into the world around us. But what does it signify? With me to discuss the Fibonacci sequence are Jackie Studdle, Junior Research Fellow in the History of Mathematics at the Queen's College, Oxford, Ron Knott, Visiting Fellow in the Department of Mathematics at the University of Surrey, and Marcus Giussotoi, Professor of Mathematics at Wadham College, Oxford. Marcus Giussotoi, the Fibonacci sequence named after a 13th century Italian mathematician. He was Leonardo of Pisa at the time. Can you tell us a little about him?
Yeah, he's an incredibly important person, really, in the history of mathematics, because Europe before Fibonacci really was in the Dark Ages mathematically, definitely. I mean, they were still using Roman numerals. They hadn't got the developments that had been happening in the East. India had developed these wonderful numerals, 0, 1, 2, 3, up to 9. And it's Fibonacci who actually learnt about this and brought a lot of these ideas to Europe. So he's a key sort of linchpin in the whole history of mathematics. And he learnt it actually by travelling in northern Africa with his father, who was collecting taxes and a merchant for the state of Pisa. And so it was there that he actually became aware of the exciting developments that had been happening in the East mathematically. And it's you mentioned actually in your opening that maybe the numbers shouldn't be credited to Fibonacci, and actually you can find in India the discovery of these numbers much earlier, say in the 6th century, related to rhythms. I mean, actually mathematics and music were very connected in India, and these numbers actually can be used to count how many rhythms there are, where you have, if you've got long and short beats. So, for example, in poetry, the number, if you've got 4 bars, 4 beats in a bar, how many different rhythms can you fit in with long beats and short beats? Well, you could have 2 long beats, 4 short beats, or long, short, 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 long, short, 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 long. Well, that's 5, and that's a Fibonacci number. And you find that actually these numbers were used and discovered in India to be able to count the number of rhythms. So it may be that Fibonacci had also been aware of these numbers through his travelling in northern Africa, and but he is really seen as the beginning, I think, of mathematics in Europe, because he brought these ideas to Italy from the northern Africa.
We've talked about numbers developing in India and then going into the Arab world. What about the Fibonacci sequence itself? Can you tell us a bit more about where that might have come from?
Yes, yeah. Well, I mean, he describes it in a book to do with a problem about rabbits. I mean, which I'm sure we'll come on to. But the idea is that this is a natural sequence about growth, and I think. Actually, this idea of Indian rhythms is a nice place to look at it, because if you want to know how many rhythms there are with a certain number of beats in the bar with these long and short things, well, it's built out of the numbers that you've built on smaller bars, smaller. When you have, for example, if I want to count how many rhythms there are with 5 beats in the bar, that's built out of the ones with 4 beats and 3 beats, because you add either a short beat on the end of that or a long beat. So the Fibonacci sequence is got by adding the 2 previous numbers together. I guess we haven't actually said that. That's really important. The Fibonacci sequence, how do you build it up? Well, 1, 1, 2, 3, 5, 8, 13. You get the next number in the sequence by adding the 2 previous numbers together. So it's a sequence which is very much to do with growth. What you've got, the information you've got beforehand, the 2 numbers before the number you're trying to work out, are used to get the next number in the sequence. You add those 2 together to get the next number. And that's why we see it in so many different problems, because it is about growth, learning from what you've done before to get the next piece of information.
Jackie Studdle, he wrote his knowledge into a great book called the Liber Abaci, the Book of Calculation. It's published in 1202. Can you just give us some overview of what was in that book? Because the Fibonacci sequence was only part of it, but he was bringing vast tracts of new mathematics to Europe.
Yes, he was.
Tranches, I should have said, not tracts.
Yes. I don't quite agree with Marcus that Europe was in the Dark Ages before that. Islamic Spain had a very rich mathematical and scientific culture for 2 centuries before Fibonacci brought this work to Europe. But his book was important in spreading these ideas and in writing them as a textbook, really. It's the first European textbook in mathematics. It's an enormous work. The modern English translation has 600 pages, so imagine that written by hand in manuscript. It's a very large work. The beginning of it is introducing the Indo-Arabic numerals. The very first line of it introduces those numerals and explains to you how to write them and how to calculate with them, because you need to know not just how to write them, but
1,
the
2, 3,
special...
4, 5.
Well, he writes them 9, 8, 4, 5, 6, 7... he writes them backwards in the Arabic way. But he has to explain to you how you add, how you subtract, how you multiply, using place value, which comes with the numerals.
Can you just explain place value a bit more?
Yes. If I write the number 666, 666, the first 6 stands for hundreds, the next 6 stands for tens, and the final one is units. So according to the place that the digit takes, that tells you something about the size it's representing. And it means you only have to learn 9 digits plus 0, and then you can do all the arithmetic you want to do. So it's a very powerful system.
So he started with that. What else did he develop inside this great book?
Well, after 7 or 8 chapters on teaching you how to use these numerals, he then goes on to lots of practical calculations. There are lots of problems in commercial arithmetic, for instance. For instance, if you buy so many yards of cloth at such a price, how much will it cost you to buy so many other yards? That kind of problem. Also converting currencies, because at that time every town had its own currency, more or less, so you needed to know how to convert currencies between different places. Lots of problems of that kind. And then there's a long chapter on recreational problems, and that's where the rabbit problem comes.
Sorry.
There's more. I mean, after that there's a very short chapter on algebra and there's a very short chapter on geometry. So it's really a compendium of the known mathematics of the time that he'd gathered from his travels in North Africa and the Middle East.
You pointed out that some of this had been going on in Islamic Spain for a couple of hundred years, but would it be true to say that Fibonacci brought it to Europe in a more general and a more influential manner?
He brought it to Italy. I mean, Spain was enormously influential, and lots of material that eventually found its way to Northern Europe actually came through Spain, not through Italy. Fibonacci's book had a relatively limited circulation, but it was important because it certainly spread the numerals through Italy and eventually into France and Germany.
Ron Knott, in chapters 12 or 13, or so I've been told, I have not read this book, Abaki, Fibonacci sets out various problems which are in need of mathematical solutions. One problem he talks about it is the Fibonacci sequence, and he uses rabbits as an illustration. Can you bring the rabbit... I'm not going to say bring the rabbit out of the hat. God.
Yes, it's about doing what rabbits do naturally, and he's just introduced the idea of perfect numbers, and this big chapter that Jackie mentioned, it's about a whole quarter of the book after the things that we now learn in primary school. And it looks as if it might have just been perhaps an arithmetic exercise, because although it's about rabbits, that you put a pair of rabbits in a field and they can reproduce after 1 month, and each month after 2 months, and each month they then produce a pair. And so he says, if I put a pair in an enclosed field, how many will there be in 12 months? Well, each rabbit continues to the next month. We're assuming there are no foxes around or other diseases that we hear on the news these days. And so he says that after 1 month you've still got your original pair, they produce another pair. And then the next month the original pair have produced a new pair, and the pair that were there from the month before now become reproductive. And so you get one pair, and then the original pair plus the new pair, 2. Then the original pair plus a new pair, and the original one, 3. And it goes on that way, and at the end of... and these are the numbers. He says each month is the sum of the 2 before. It's the sum of the 2 before because all the rabbits that were alive the month before are still there. And then all of those that were alive 2 months ago are the ones that are reproducing. So for each one of those you get a new pair. So it's the sum of the last month and the new ones from the month before. So that's why you sum the 2 before. And you're starting with a pair when you start and a pair when they're a month old. You start from 1 and 1. And it builds up in that way. And it's just a very small problem in this huge chapter, as Jackie said, on all sorts of practical problems about ploughing fields and cloths and things.
And they end up in here with 377 pairs.
That's right, yes. 1, 2, 3, 5, 8, 13, 34, 55, 89, 144. Is it there he stops, or the next one I've forgotten?
So this is just a small bit of one chapter, this?
Yes, it is. It wasn't a very significant one. It was only later on a French mathematician, Edouard Lucas, writing in the 1800s, who wrote mostly about the sequence, and in fact gave it its name. It just wasn't known as the Fibonacci sequence. It's one of many sequences like the perfect number in the chapter before, sequence of perfect numbers. And he was the one that gave it its name, Leonardo of Pisa. He calls himself Fibonacci. We're not sure whether that means the son of the Bonacci family or the son of good fortune, but that's the name that stuck from the 1800s.
Why did it take so long to get out and get taken up?
Well, it was known before. Lucas looked at the mathematics of it, and another similar sequence. Instead of starting with 1 and 1, you start with 2 and 1, and you get a different sequence, and it's called the Lucas numbers, 2 and 1, with the same principle. 2 and 1 make 3, 1 and 3 make 4, 3 and 4 make 7. And those two are very much tied up mathematically, and that's the name of, that sequence has his name. But they were known beforehand. Kepler writes about them in the 1600s. He hints at the idea of patterns in the vegetable kingdom, as he calls it, and that and he writes about the golden section as well, which again is another number related to this series. Maybe we'll come on to that later. And but they're all very much linked together: the Fibonacci numbers, the Lucas numbers, and the golden section pair of numbers, really.
Well, let's look at the golden ratio with Marcus Jusoto. This golden section, golden ratio, how do you get it out of the Fibonacci sequence, and what does that signify?
Yeah, so you get it, if you look at the ratios of one number to the previous number, so for example 8 over 5, and you keep on doing this, so let's take the next one, 13 over 8. So these fractions, as you go through the sequence, converge more and more on a special number which we call the golden ratio. And the golden ratio has been studied since the ancient Greeks, and it expresses what we sort of believe as the perfect proportions for a rectangle. The golden ratio, a rectangle is in the golden ratio if the ratio of the long side to the short side is the same as the ratio of the sum of the two sides to the long side. And it's a very sort of aesthetically pleasing sort of ratio. And, I mean, one starts to find it sort of everywhere. I mean, people find it too many places, I think. But, for example, the Parthenon is believed to be constructed in this beautiful ratio. And a lot of frames in the Louvre, for example, like this sort of shape. They don't like squares. They like this rectangle.
And postcards.
And postcards, so you do find it in a lot of places. Ron's showing me his ticket from the train. Apparently, that's in the golden ratio as well. So your credit cards and things like that are probably. There's this relationship then between this very special ratio and the Fibonacci numbers, because the ratio of the one Fibonacci number to another as you go through the sequence converges on this golden ratio. And it's a very important relationship between these, because what mathematicians want to do is to find efficient formulas, for example, for calculating the Fibonacci numbers. If I want to calculate the millionth Fibonacci number, I don't want to have to count all the pairs all the way up to 1,000,000, because that's terribly inefficient. We're very lazy at heart, mathematicians. So the golden ratio gives you a lovely formula. You take powers of the golden ratio, essentially, and you can use those to get the millionth Fibonacci number without having to do any work at all. So if you're actually calculating and wanting to know what Fibonacci numbers are, the golden ratio is extremely important in capturing them.
Jack, instead of what Marcus has mentioned, the Greeks, the ancient Greeks as we keep calling them, knowing about the golden ratio, what did Euclid write about that?
Well, the construction that Marcus is talking about appears in Euclid, in Book 6 of Euclid, where Euclid sets as a problem, how do you divide a line into two segments so that the ratio of the whole line to the longer segment is the same as the ratio of the longer segment to the shorter segment, which is exactly what Marcus was describing. And this is quite a difficult construction in Euclid, but he tells you how to do it. He explains how to do it. And it became very well known. It was known as dividing a line in extreme and mean ratio. But all later mathematicians knew this, because they knew Euclid very well, of course. So it's there. I'm not sure that Euclid calls it the golden ratio. I don't know where the term golden ratio comes. Plato knew about it and talked about this particular ratio.
What's your view of the notion that buildings like the Parthenon followed this ratio?
I don't know. As Marcus said, I think people can see this ratio too often in too many things. It does give pleasing proportions, so maybe people just built in pleasing proportions, and that happens to be close to the number we now know as the golden ratio. Whether they actually had that in mind as they built is doubtful, I would say, but I don't know.
But does it suggest that if they didn't have Euclid in mind, the fact that they did build something which does seem to follow those proportions means that it's instinct in human beings, doesn't it? I mean, I'm just asking.
Yes, yes, it's certainly an instinctive proportion.
So where does that come from?
I don't know. I'm not a psychologist.
I think you can see that it's again about this way of growth and building things up, because you can build this this perfect sort of rectangle by using the Fibonacci sequence in a way. I mean, you take a sort of a 1-by-1 box, and then you add on the side of that another 1-by-1 box. So now you've got a 1-by-2 sort of building. Now what do we know about? Well, we've got the number 2, so let's add a 2-by-2 box onto that. And so now I've got a 2-by-3 box. Well, I've got 3 now, so let's add a 3-by-3 box. So now I've got a 3-by-5 box, and you can build up what's actually sort of a spiral of boxes, and that is actually, that natural thing is growing into a rectangle, which is getting closer and closer to the perfect to this golden ratio. So I think it naturally.
But a building like the Parthenon wouldn't have been constructed on those
Absolutely not, but I think that's why we're naturally drawn to this sort of shape, because it has this growth in it, and that's why you start to see it all over nature as well.
Ron, Euclid, I'm told, I read, seemed to relate the golden ratio to the 5 Platonic solids. Now, can you take us into that?
Yes, these appear in the Euclid's Elements as well, and some people think it was sort of, well, one of the aims of Euclid's 13 books was to describe the 5 shapes that Plato had mentioned, which are the most symmetrical 3D shapes. In other words, if you're trying to design a dice, in other words, so you want all the edges to be the same length, all the angles to be the same, and the faces to be identical. And so the usual shape we use is 6 squares to make a cube. But there are 5 shapes. The simplest one has 4 faces, which are regular triangles, 4 faces tetrahedron. The next one is 2 square-based pyramids glued together on their squares, and that makes 8 triangular faces, the octahedron. There's the hexahedron, the cube. And there are 2 other ones. There's one with 20 faces, triangular faces, called the icosahedron. And then another one with 12 pentagonal faces called the dodecahedron. And these are the 5 most symmetrical ones. And if you look at the mathematics of the icosahedron and the dodecahedron, that's full of ratios to do with the golden section. In fact, if you describe the coordinates of these shapes as we might do in a Descartes system, in an ordinary 3D coordinate system today, the tetrahedron, the cube, and the octahedron just have ones, plus ones and minus ones. The icosahedron and the dodecahedron, you also add on multiples of, you also add on the golden sections, these 2 numbers, pluses and minuses, and that gives you the shapes.
So he was thinking about that at the same time. So they were onto that at that time. Much the same, or was the Fibonacci sequence a refinement?
Well, I think it's interesting with I think the golden ratio, you see, was around before the Fibonacci sequence was ever around. I mean, and I think it reflects actually the ancient Greeks were more interested in geometry and ratios of lines. And I mean, I think you can even find this golden ratio in just a simple pentagon. And the pentagon, of course, was a very sort of spiritual figure amongst the Pythagoreans, and so it's interesting that then you get the numbers, these Fibonacci numbers, starting to mix in much later, sort of medieval time, and then there's this sort of connection between geometry and numbers, which is actually a very late sort of idea. I mean, that's really what Descartes did, was to fuse geometry and numbers. Before that, they were not really seen as 2 things together. So I think it's quite an exciting moment when you see the Fibonacci numbers actually giving rise to geometry.
Jackie?
Yes, I agree. I mean, this is the extraordinary thing about it, that the golden ratio was known for a long time. The Fibonacci sequence is a quite separate development. It comes from separate roots. It comes from Arabic and Indian roots, whereas the golden ratio is coming out of Greek mathematics. And tying these 2 things together is very interesting. I don't know when it was first discovered that these 2 went together. I might just say the ratio that Marcus is talking about, if you calculate it, it's a number that begins 1.618, I think, and goes on. It's an infinite decimal. There's an exact expression for that. It's 1 plus the square root of 5 divided by 2, which the Greeks would have known. They would have known it in that form, which is a very precise measurement. So,
And which also is interesting because it's an irrational number. So although the Fibonacci numbers are giving you fractions, they're the fractions which approximate but never quite meet the golden ratio.
Yes.
So.
And in fact, they give the best approximations as well to the golden section. If, as Marcus said, if you take the ratios of the numbers, the larger over the smaller, you'll get, it tends very quickly to 1.618, blah, blah, blah. But if you take the smaller to the larger, you'll get 0.618. And the interesting thing is it's exactly one larger, and that's what defines these two numbers very precisely, and in fact makes them unique.
The Euclid, we'll stay with Euclid for a moment, Marcus Soto. Mathematician Luca Pacioli published On Divine Proportion 1509, as I'm told, illustrated by his friend, we think, Leonardo da Vinci, and that we have the golden ratio in that. Can you tell us about how he went over, if you believe he did, into painting?
Well, there are certainly sketches that Leonardo made, which Leonardo da Vinci, rather than Leonardo da Pisa, which seem to indicate that he was setting up proportions, for example, in faces, that he, and this is another place where you find, if you want to, the golden ratio is in proportions of the structure of the face. So you can see that there was Leonardo da Vinci had a lot of mathematical background, so he drew a lot of these Platonic solids, for example, as an exercise in perspective. But I think, again, what you find is a square. If you have a square, your eye is naturally drawn just to the centre of the square. And that's kind of uninteresting, actually. But if you have a rectangle in this golden ratio, there are other focal points, partly due to this sort of Fibonacci spiral that you get with these sort of squares that I build up, the sort of shape. That there are natural places in a picture that your eye is drawn to, which aren't the most obvious places you might think. And so, and if you look in pictures of done by something like Leonardo da Vinci, you find these four focal points, interesting things happening there. Now, again, you might say, well, is this just somebody who's intuitively drawn to that, or have they actually programmed this in and constructed a picture which has these focal points because he knows that the golden ratio naturally draws you to these 4 points, so you put something interesting in those places?
Would it be fair to say, Jackie Studdle, that mathematics in this period was underpinning, to some extent, aesthetics?
I think it's difficult to say. As Marcus says, you don't know how deliberate these things were, whether this is an instinctive thing to do because it's pleasing, naturally pleasing, or whether there is some deliberate construction going on.
Well, if we took the Last Supper, which everybody will know, that's been called following these the rules of the golden mean. Can you tell us if you think it does, or if it could have been arrived at naturally in inverted commas, or naturally without any inverted commas?
I really can't say. I think you can't say unless you know what the painter had in mind at the time. It's impossible to know whether it exists.
I would suggest. I think that they were so aware of mathematics because of the perspective and how that worked, and that relied on a lot of mathematics. They were full of Platonic solids in these paintings around the time, and so they would have known about things like the relationship of Platonic solids to the golden ratio. That I think yeah, but again, speculation. But I will come off the fence and say I think they probably did know what they were doing.
I won't come off the fence.
No, I think I'm with Jackie as well. I think when you look at pictures, there's so many lines you can draw, and somewhere in there you'll find one that's more or less around 0.618. Now, whether that's deliberate or it's a product of psychology, maybe I'll sit on the fence.
But I think certainly in more modern times, you find a lot of artists, composers, and things deliberately using all these things. So
yes,
I mean,
there's
certainly maybe we can't say anything about that time, but we know now that a lot of composers and architects and Salvador Dali certainly was deliberately using the golden ratio in some of his work.
And Corbusier as well, yes.
Yeah.
Can we, Ronald, can you tell us about the math? We touched on with a hung jury on the aesthetic question, but what purchase did it have on other areas of mathematics?
The Fibonacci?
Yes.
Well, around the in the 1800s, Victorian times, there was a lot of interest in kind of unifying mathematics and finding theories for things, and there was quite a lot of interest in. They'd noticed that the Fibonacci numbers appear in nature, in plants as opposed to animals, really.
Yeah.
And so it was, for instance, if you cut a tomato across the middle, you'll find it's in 2 or 3 segments. But look on the outside, and there's a little green bit which has got 5. 4's missing. If you look at a cauliflower, and the florets are actually in little spirals. There are about 5 spirals in one direction and 8 in the other. If you look at a pineapple, there are 3 fairly obvious sets of spirals on the outside. One of them's 5 spirals going around fairly shallow, 8 are a little bit steeper, and 13 steeper still. It's these particular numbers. 4 is missing. It's not very often there in the world of nature. So when you're looking at the food we eat every day, this is a series you're eating every day, and you're getting your 5 a day. It puts the phi into Fibonacci, the phi into fibre. And it seems to be that it's to do with the packing problem, that if you're trying to arrange leaves around a stem, you don't really want them to overlap and cut out the sunlight or not catch the rain. Or if you're arranging seeds on a seed head, you really want an efficient packing. And it was it was only proved relatively recently in the 1990s that the best form of packing is to do with arranging seeds with a golden section. You put 0.618 seeds per turn. It's as if it's a little rotating stem. This is the original stem cell at the end of a stem, and where the plant grows. And it's as if it goes 0.618 of a turn and produces a new stem cell, which might become a leaf or a branch or a seed or a petal. And then it goes another 0.618 and so on. And when you plot that out, quite magically, the human eye picks up spirals. Near the middle there are spirals in 2 directions, 3s and 5s, 5s and 8s, 8s and 13s. And then the mathematicians have proved that that's the most efficient packing, no matter how large you go. There are no sort of seeds squashed in one direction with spaces in another. So mathematically it fits into nature, and there was a lot of interest in that before it was proved, around the 1900s as well.
Jackie, do you want to take that up and speculate as to why you think... I know, but no commitment is required, but speculate as to why you think that this recurs. This sequence recurs.
The sequence. Well, I think Ron's explained it very well, that mathematically, certainly in seed patterns, it gives you the best packing of the seeds, and the most efficient way for the plant to grow and
I think
to
it again
reproduce
relates
itself.
to this way of the building up this spiral of squares. I mean, if you think a cell starts off with just one cell, and then it has to add something, so it adds this other cell, and you get the 1, 1, and then you add it's sort of grown and it needs to enlarge. And actually, this is why you see the Fibonacci numbers coming up in the way that snails grow. I mean, the spiral of a snail actually has the Fibonacci numbers embedded in them as well. And if you take these squares and you build them up and draw a sort of spiral through it, you see a sort of natural shell appearing. I mean, the other one that we have to mention is, of course, petals on flowers. I mean, that again seems to always be Fibonacci numbers or a double a Fibonacci number. I mean, it's very rare plants which actually don't have Fibonacci numbers. And if you do go out to the garden and test it in the summer and it hasn't got a Fibonacci number, I bet you it's just because the petal's fallen off the flower, and it's which is how mathematicians get around exceptions. But,
yes, it is. It certainly is prevalent there in nature, but actually in the plant kingdom, not so much in animals. With animals, we've got this bilateral symmetry, the mirror symmetry, which is actually very rare in flowers, and that seems to be the distinguishing. And we can't find really the golden section number very much in animals, but and it's usually the series. But then again, you look at a fuchsia, which has got 4 petals, or a daffodil, which has got 6, and those aren't the Fibonacci numbers.
The explanation for that, I've heard anyway, is that it's a double flower, basically. That it's a 3 on a 3 and a 2 on a 2. We can find any way to get around these things. So.
That can be if you're an ardent Fibonacciist.
Yeah. Well, somebody did send me a picture of a flower which had 7 petals on, and that I can't do. Yes. I can't get around that. So I give up with that one.
When you say it's not in the animal kingdom, of course, there's the very famous drawing by Leonardo of the man in the pentagon.
That was Vitruvian, his picture of Vitruvius's description. But Vitruvius's description is very much, this is the one you see on the front of pads of paper, the man in the square and the circle, but it's very much to do with fractions. He goes a little scale at the bottom to show that it was designed with fractions. The whole thing about the Fibonacci numbers and the golden section is that it's an irrational number. These fractions are the best ways to get at it, but it's actually not a fraction.
You've described the reason for it in terms of packing. These numbers pack well, as it were. Are there any other reasons being put forward why that numbering sequence should be so widespread? Or just, I mean, you put forward a very utilitarian one. We would like a little mystery and magic in our mathematics.
Well, in fact, if you look at cactus and succulents, it's quite often to find the arrangement of the spines is sort of 4s and 7s, 7s and 11s. And in fact, that gives us another sequence starting with 1 and 3, 4, 7, the same principle, add the latest 2 to get the next 11, and that gives us these Lucas numbers. Those appear, but the thing is, no matter what two numbers you start with any pair of numbers and keep adding those to get the next, and adding the latest 2, all of them get to the golden section. And it seems to be the mystery is the golden section is behind this, which manifests simply in the Fibonacci numbers, but also the Lucas numbers. And
well, I think it's an important point, because mathematically this is a very important idea. This is called a recursive sequence, because you use the previous numbers to build the next one in the sequence. So the Fibonacci is the most simple version of that. You use 2 previous, add them together to get the next one. But in mathematics, certainly in the 20th century, we've been looking to find more complicated versions of this in many sequences of numbers. I mean, in my own work, I deal with trying to count numbers of symmetries. But what I'm trying to do is to show that there might be a similar process to build my sequence of numbers. They're very nice sequences because you get very explicit formulas for them. And so Fibonacci just kicked off, or this sequence kicks off, a whole way of looking at number sequences, which we're trying to find Fibonacci in as many sequences as we can, or that style, recursive functions. So it is a very important mathematical idea.
Jackie?
Well, there are many very beautiful properties within the sequence itself as well, apart from in relation to plants. I mean, just looking at the numbers themselves, for instance, if you take the consecutive numbers 2, 3, 5, if you square 3, you get 9. If you multiply 2 and 5, you get 10, which is 1 more. This happens all the way along the sequence. If you square any of the numbers, it's 1 more or 1 less than the product of the numbers either side. And there are many, many, many such properties.
I mean, it's just amazing.
Absolutely fantastic.
Which is why there's a whole journal, the Fibonacci Quarterly, which is dedicated to discovering all these weird and wonderful things.
Could we have some more, please?
Well, Ron's the expert.
Well, that's one.
Well, the other one is if you start from 1 and 1 as your indexing sequence, so the first Fibonacci number is 1, the second is 1, the third is 2, the fourth is 3, and so on. Using that number sequence, then since 3 divides into 6 as just numbers, then the third Fibonacci number, 2, divides into the sixth, which is 8. And this happens whenever, if you start with that numbering system. So in fact, the Fibonacci numbers in the prime positions are the ones that become important. And in fact, this relates to Marcus's work, because each of these is distinguished by a very unique prime, which is itself a divisor of this Fibonacci number. It acts as a kind of marker all the way through, and then it relates to get you into prime numbers.
Of course, there's an open problem, which is are there infinitely many Fibonacci numbers which are prime numbers, indivisible numbers? We don't know that. 13, for example, is a Fibonacci number and is also an indivisible prime number. But that's an open problem about Fibonacci numbers.
What does that mean?
Are there infinitely many Fibonacci numbers?
No, but what does open problem mean?
Open problem means that we don't know.
Oh, right.
Yeah, it means that... I see what you mean, yeah.
Far more elegant. I'm going to use that.
Yes, an open
That's
problem.
an open problem.
Yes, we haven't closed it.
Rather than I haven't a clue.
So I think it
But
probably
why
is...
don't you know? I mean, if you can calculate the Fibonacci ad infinitum, why don't you know?
Very good, because I'm a finite being, and therefore, I mean, that's a very fair point. You see, the mathematicians are finite beings at heart, and to be able to analyse an infinite sequence like this, we have to find clever ways to show why infinitely often a prime will pop up, and this is a mystery. The other interesting place, I think, where Fibonacci numbers come up is actually in generating Pythagorean triples. Pythagoras' theorem is about right-angled triangles. So you can build a right-angled triangle with a side which has short side 3, next side 4, longest side 5 units. 3, 4, 5 is called a Pythagorean triangle. But if you want other examples of triangles, right-angled triangles, each of whose sides are integer lengths, actually, it turns out that the Fibonacci numbers are a wonderful way of generating these triangles. So it shows that these Fibonacci numbers are just embedded everywhere. They're embedded in geometry, they're embedded in nature, and also aesthetic things like music, architecture, and...
Which comes back to the... if it isn't... Probably isn't a record, but it's a fairly accurate paraphrase. Galileo said, I discovered the book of the universe, it's written in the language of mathematics. That's what you seem to be saying now.
Yes, I think so. I think that nature is built by very simple operations, which can produce things with immense complexity. And Fibonacci sequence is a very simple way of generating growth. and yet suddenly you have just a very rich sequence.
Ron, you mentioned earlier Le Corbusier, and you said, and Jackie firmly fence-bound, would not come up the fences whether they'd known about the gold mean when they did the Parthenon, or whether Leonardo really knew about it. But when we come to the modern age, then people are taking it on. Can you tell us how Corbusier take it on and incorporating it and making it central to their work, self-consciously?
Yes, it was again, it's the early 1900s, and he wanted to design buildings which had a human feel, of human proportions. And so he had this sort of model of the human, which is that if you look at the position of your belly button, your navel, it's about this golden section point further up, and if you raise your hand, well, if you look at your arm, the length of your hand to the length of up to the elbow looks as if it's about a golden ratio, and the elbow to the arm. And so he kind of formalised that in a structure called the modular, and he used that to sort of tell his architects to design buildings. On the other hand, he did say, but if it's not working, if it's not really fitting, then abandon it. But it certainly, he was trying to use it as a guiding principle in designing buildings.
And once the as it were, the Fibonacci sequence came out, which was centuries after it was in this original book, it was taken up or developed. There's a Scottish biologist called D.W. Thompson on growth and form in 1917. How did he come in on this? In this argument? Yes,
he wrote a book on growth and form, again looking at the 1900s when they were trying to find principles behind things, major principles. Marcus can tell us probably about the Hilbert programme later on for mathematics, when they were trying to, and that led to a whole growth of mathematics in the 1900s. He was writing about patterns of can you take the shape of a horse's head and relate it to a sheep's head? They're similar. There's a small deformation. And he wasn't the first to write about this. It relates to a book really by Church, who was the first person in about 1910 to formalise shapes of objects in nature. And then there was a big chapter in there about the golden section and the Fibonacci numbers. They didn't know quite why they appeared, but they were noting they were, and the properties. And there's one other interesting property we haven't mentioned about the golden section, which I call Phi, or it's usually called Phi after Phidias, the architect who designed the sculpture in the Parthenon. And that if you take the powers of the Fibonacci, you can add the two powers, the squared plus the cubed power adds to give you the fourth power. The third and the fourth power add to give you the fifth. Well, you'd expect a multiplication, but you can do it with an addition. And again, that's a very distinctive property of these golden section numbers, and perhaps is why it's there in nature. It can do multiplication by addition.
Do you see, is it too fanciful? I'm certain it is, Jackie. I'm looking away as I'm speaking. The fact that it appears everywhere, it appears in many, many places, does it suggest some sort of a Platonic attribute, that there's, as he would say, a divine form behind all this?
That is too fanciful for me. I can't go there. It's not the sort of thing I can speculate about. Can I turn the question or the conversation around? Because I'd actually like to ask a question of these two experts, please, since we have them here, which was when the Fibonacci sequence was rediscovered, as it were, because Fibonacci's book the text wasn't published until the 19th century in Italy. Until then, there would have been early manuscript copies, but no printed editions. So where did people learn about these numbers, or were they rediscovered independently by Lucas and others?
The numbers themselves, it's just a very small problem. The main thing is, as you said, the book is about arithmetic that we learn in primary schools now, and the numbers, and that certainly went across Europe and everywhere, so it was quite influential.
Well, I guess Lucas probably
But where did Lucas find it, or did he rediscover them for himself?
That I'm not sure. It's a French book. I've tried to find a copy of the book and I can't. It's quite difficult.
Well, again, Lucas would have been. I mean, these Lucas numbers, which are built in a similar way, are of course very important for testing Mersenne primes, and that's how you get. So there are lots of. The point is that because they crop up so many places, there are loads of. I think the other interesting place we must mention is music. I mean, architecture. It's sort of you can see that the way things are being built. Boxes being put together. You can see the Fibonacci sequence, but I think the interesting thing is people like Bartók and Debussy who are threading it, and I think, again, deliberately. You see these numbers in those sort of bars that they're building up the piece of music. And again, it's this idea of starting with something simple, which a piece of music generally does, and developing themes, and they're very naturally drawn to the Fibonacci sequence as a structure within which to write. I do some work with a composer called Dorothy Carr from New Zealand, and she has a piece which just has the Fibonacci sequence as its skeleton written, the cello piece, and she loves it because she sees the way it builds on the two things which have gone before, build to create the next piece, and so I think actually a student of mine yesterday told me even a band in America called Tool use the Fibonacci sequence. So in music it is a nice structure that, again, because there's this aesthetic sort of growth and climax in it, I think.
Do you think, Jackie Settle, that more discoveries are going to be made about and through the Fibonacci sequence? That it's going to yield entrances to other areas?
Undoubtedly. I don't think we certainly haven't come to the end of all that can be known about it or through it. And as Marcus said, there are open problems. There are still problems there. But,
I mean, I'm trying to prove that my numbers are basically like Fibonacci numbers, but I can't do it.
Your numbers being what?
Numbers which count groups, symmetries, something completely unrelated. But some of the theorems I have proved are showing that the structure of these numbers are very similar to the ones that Fibonacci do. So, for a modern mathematician, this style of mathematics is really important.
Yes, the Fibonacci Association in America has a journal that comes out, but every 2 years they have an international conference. I've been to them for a few years now, and it's quite interesting to see still the development of new ideas in here. And I was talking to a firm in California who are using the shapes of these seashells with the Fibonacci, with the golden section spirals. They've taken the centre of one of these and made it into a rotor. And it turns out to be about 30% more efficient than any known rotor. They've been patenting this for a few years. And just this very small rotor I saw in a huge tank just sort of rotates a tank. It's designs based on nature, which seems to have new applications.
And they've even found their way into popular culture, of course, because anyone who's read Dan Brown's Da Vinci Code, the first code you have to crack is the Fibonacci numbers. So, I think they're really in the public imagination. So, what better advertisement do you want than, how important these numbers are?
And there's now an English translation at last of the Liber Abaci, so anybody can read this for themselves and all the other wonderful things that are in the book.
Well, thank you all very much. Thank you for guiding me through that. No, I was fascinated. I just hope I can remember it. Next week...
It's very simple. You just add the two previous ones.
I can remember that, but all the other stuff you've said. Anyway, thank you very much.